were discussing balanced homodyning in the last class. So today we will discuss a little more details of balanced homodyning and look at some examples of how this process helps me to differentiate between squeezed states and any state which is not squeezed, like the coherent state is not a squeezed state. So this particular method is a very useful method to demonstrate and to measure certain non-classical features of light. Do you have any questions from what we have discussed in the last class? Okay, so we continue. Let me recall. In balanced homodyning, what we are having is we have a 50% beam splitter. The arm 1 is the input state, which is an unknown state. In arm 2, we put in a coherent state, which is represented by alpha, which means it's like a wave coming out of a laser. A good stabilized laser will produce a coherent state. Then, in arms 3 and 4, we have light which is reflected from state 1 and transmitted from state 2. And similarly, in arm 4, we have one which is transmitted from 1 and reflected from 4, reflected from 2. Then we have two detectors here which measure these intensities coming here, and then we do a subtraction. And it is this signal that we are looking at, which I will show you contains interesting features of the state which is coming from here. So let me write down again the annihilation operators in arm 3 and 4 as related to 1 and 2. So if you recall, this is I by root 2 A1 plus 1 by root 2 A2. Similarly, A4 is equal to 1 by root 2 A1 plus I by root 2 A2. So what we are actually detecting is the expectation value of the number operator here, and then subtracting them. So the expectation value of the number operator here is expectation value between A4 dagger and A4. Here it is A3 dagger and A3, and we are subtracting. So what we are trying to do is a measurement of this operator, which is A4 dagger A4 minus A3 dagger A3. So in the last class, we substituted these expressions here. So let me just repeat that. So 1 by root 2 A1 dagger minus I by square root of 2 A2 dagger into 1 by square root of 2 A1 plus I by square root of 2 A2 minus I by square root of 2 A1 dagger plus 1 by root 2 A2 dagger into I by square root of 2 A1 plus 1 by square root of 2 A2. So if you open these brackets up, what you can show is this comes out to be I times A1 dagger A2 minus A2 dagger A1. Did I do N3 minus N4 last time?
Yes. Yeah.
Okay, so anyway, it's a difference between these two. So what these two detectors are detecting is expectation values of A3 dagger A4, A3 dagger A3 and A4 dagger A4, and subtracting the signals coming from detectors 3 and 4. Okay. This signal which is being detected also has noise, because in all this I'm interested also in how much is the noise that is being detected, because it is in the noise properties of the states which are coming here, which is what I have to show. There is squeezing, for example. It's certain quadratures of this field there is squeezing. So I also need to calculate what is the variance in ND, the difference in the number of photons being detected in 3 and 4. And for that I need the expectation value of ND square, because the variance in ND, which is the difference in photon numbers, delta ND square, will be expectation value of ND operator square minus expectation value of ND operator square. The variance of an operator is defined by expectation value of the square of the operator minus expectation value of the operator square. So I need to calculate ND square. So ND square is, this is the expression for ND which we have calculated. So ND square will be square of this, so which is minus A1 dagger A2 minus A2 dagger A1 into A1 dagger A2 minus A2 dagger A1. So this is minus A1 dagger square A2 square minus A1 dagger A1 A2 dagger minus A1 dagger into A2 dagger A2 plus A1 square A2 dagger square. We have to keep track of the ordering of the operators. The inputs at 1 and 2 are assumed to be statistically independent, so their operators commute. So I can just interchange, or I can just exchange the positions of A1 and A2. Now, the normal ordering, you remember, is with the dagger operators on the left and the non-dagger operators on the right. So I want to replace this A2 dagger by what? 1 plus A2 dagger A2, and similarly this A1 dagger I will replace. So this is minus A1 dagger square A2 square minus A1 dagger A1 into 1 plus A2 dagger A2 minus 1 plus A1 dagger A1 into A2 dagger A2 plus A1 square A2 dagger square. This is equal to minus A1 dagger square A2 square minus A1 dagger A1 A2 dagger A2 minus A1 dagger A1 minus A1 dagger A1 A2 dagger A2 minus A2 dagger A2 plus last term, which is A1 square A2 dagger square. So let me simplify this. This is minus A1 dagger square A1 A2 square plus from here A1 square A2 dagger square from here. Then I have minus 2 times A1 dagger A1 A2 dagger A2, these two terms. Then I have minus A1 dagger A1 minus A2 dagger A2. A1 dagger square A2 square plus A1 square A2 dagger square. These two are identical terms, so minus 2 A1 dagger A1 A2 dagger A2 minus A1 dagger A1 minus A2 dagger A2. Okay, so I have the two operators representing the difference in the photocurrents being generated by the two detectors, and ND square, which will help me to calculate the variance in the signal that is being detected as the difference between the detectors 3 and 4. I need to calculate expectation values. as I told you, what we use is the fact that the operators transform as represented by these equations, and we assume the states to remain the same. To calculate the expectation values of ND and ND square, I use the input states. So the input state consists of a product of this state in port 1 and alpha in port 2. This is given to me as a local, it's called the local oscillator. It's a state, it's a field which I am providing, and this is the unknown state which I am trying to characterize. So unknown state is input in arm 1 of the beam splitter. In arm 2, I input a coherent state, and we will assume that this coherent state is a strong state, which means alpha square is large compared to the expectation values of A dagger A, for example, in this state. That means the intensity of this is much higher than the intensity of this. In a standard homodyning technique, it's exactly the same. The local oscillator is a much more powerful beam than the signal. And actually, the homodyning lets you amplify the signal. So what this is doing is it's amplifying the quantum states of quantum fluctuations of this state into a classical level which can be measured by photodetectors. So I need to calculate the expectation values. So what is the expectation value of ND and expectation value of ND square? So let me calculate the expectation value of ND. This is psi and alpha in the state 2 of I times A1 dagger A2 minus A2 dagger A1 so I times, now A1 and A1 dagger operate on the size, A2 and A2 dagger operators on the alpha, because A2 corresponds to arm 2 where alpha state is incident, and A1 corresponds to arm 1 where psi is incident. So I will have psi A1 dagger psi into alpha A2 alpha, this is 2, minus alpha A2 dagger alpha into psi A1 . What is the value of this? Alpha A2 alpha. This is a coherent state. So A operating on the coherent state gives me alpha. So this is alpha, 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 which is alpha. Coherent state is defined by A times alpha is equal to alpha times alpha. Similarly, this one, alpha A2 dagger alpha will be equal to alpha star. So I can write this as mod alpha exponential I phi, where phi is the phase. This is mod alpha minus I phi. So expectation value of ND becomes I times, so this is mod alpha exponential I phi. Let me just write expectation value of this. This means that it is with respect to the input state. Minus mod alpha e to the power minus I phi A1. This quantity I am just writing as expectation value of A1 dagger. This quantity I am writing as expectation value of A1. Alpha A2 alpha is mod alpha exponential I phi, and alpha A2 dagger alpha is mod alpha exponential minus I phi. So let me take the I inside and mod alpha out. So this becomes actually A1 exponential minus I theta plus, I'll define this, A1 dagger exponential I theta, where theta is defined as pi plus pi by 2. So I is exponential I pi by 2. So when I take I inside, this is exponential I pi by 2. So exponential I phi plus pi by 2 is I theta. This minus I is exponential minus I pi by 2, which along with this gives me exponential minus I theta. So just take an I inside, combined with the exponential I phi term, and have got the expectation value like this. So actually, this is nothing but the expectation value of a1 e to the power minus I theta plus a1 dagger exponential I theta. So let me write this as, mod alpha. This is expectation value of a1 minus I theta plus a1 dagger e to the power I theta. So let me write this now as 2 times mod alpha times, I multiply and divide by 2, now what is this quantity here when theta is equal to 0? The quadrature x. Remember, x was defined as a plus a dagger by 2. If you have the electric field, if you go back and look at the electric field operator, it is in terms of a and a dagger. Then we wrote the electric field in terms of x and y quadrature operators. X quadrature operators is a1 plus a1 dagger by 2. So theta is equal to 0. This operator is x operator, and theta is equal to pi by 2. This is minus I, this is plus I. If I take I in the denominator, it becomes a1 minus a1 dagger by 2i, which is the y operator. So this, let me define this as, so x of 0 is x operator, x of pi by 2 is y operator. So already you see in the detector signal, which is being detected as the difference between N3 and N4, that signal will either give me expectation value of x or expectation value of y, depending on the value of theta I choose. And theta is nothing but phi plus pi by 2. And phi is what? The phase of the coherent state that is coming in arm 2. So if I appropriately choose the phase of the local oscillator, which is in arm 2, which means if I choose appropriately phi, then I can vary my theta, and depending on the value of theta I choose, the signal that I am measuring is proportional to the expectation value of x or expectation value of y. What has happened is, because I have given a reference phase, which is the local oscillator, I am able to measure either the x quadrature or the y quadrature. So the expectation value of the signal that I am measuring is proportional to expectation value of x if I choose theta is equal to 0, and if I choose theta is equal to pi by 2, I measure the expectation value of the y operator, of the quadrature, y quadrature. And this is interesting because now I will show you that the noise in ND square, that is variance in ND, is also proportional to the variance in the x quadrature and the y quadrature, depending on the value of theta I choose. So for that I need to calculate expectation value of ND square. So I have already got expression for ND square. So I need to calculate expectation value of ND square. Okay, here it is ND square. Let me write it below. Okay. Here is ND square. So expectation value of ND square minus, now this is expectation value of A1 dagger square. What is expectation value of A2 square for the coherent? Alpha square. So mod alpha square exponential 2I phi, because alpha is alpha mod exponential I phi plus expectation value of A1 square into mod alpha square exponential minus 2I phi minus twice expectation value of A1 dagger A1. What is expectation value of A2 dagger A2 for coherent state? Mod alpha square minus expectation value of A1 dagger A1 minus mod alpha square. These expectation values are being taken with respect to the state incident on arm 1, which I have not defined yet. It could be vacuum, it could be squeezed vacuum, it could be coherent state, it could be squeezed state, it could be number state, whatever state. So these expectation values have to be taken with that state. Now let me assume that this, what is this? This is the expectation value of the number operator for the input state 1 in arm 1. If my coherent state is very strong, this will be negligible compared to mod alpha square. So I neglect this term and I get minus mod alpha square into, okay, let me take the minus sign also inside. So this is A1 dagger square this is 2I theta, because please note minus 1 is exponential I pi and that is exponential 2 times I pi by 2, and if I add with 2I phi I get exponential 2I theta plus A1 square exponential minus 2I theta minus 2 times A1 dagger A1 minus 1. I have neglected this term and I have taken out mod alpha square out. So these are plus and plus, sorry. I have taken the minus sign inside. This minus with exponential 2I phi gives me exponential minus 2I theta. This minus 1 with exponential minus 2I phi gives me minus 2I theta, and this is 2A1 dagger A1 . Okay. Okay, so I've got expressions for the expectation value of ND and expectation value of ND square, and from here I can calculate the variance, which is expectation value of ND square minus expectation value of ND whole square. Now let's look at some examples. Okay, so the first example I want to consider is that in arm 1 I don't put anything. I don't have any incident wave in arm 1. So what do I represent psi as? So the first example is where I have, here is alpha coming. So what is input state here? Vacuum state. So psi, and this vacuum state satisfies this equation. E operating on 0, 0, 0. That's a vacuum. Coherent vacuum state. Standard vacuum state where none of the modes are occupied. Because after this we will consider the squeezed vacuum state. Okay? So now let's calculate expectation value of ND and expectation value of ND square, and from there the variance. So what is expectation value of ND? This is 2 times mod alpha times expectation value of A1 exponential minus I theta. So this is 0 plus A1 dagger e to the power I theta by 2, 0. How much is this? A1 operating on 0, 0. A1 dagger operating on bra 0, 0. The difference signal is 0. There is no difference signal. There is signal in arm 3 and there is signal in arm 4, but the difference signal average is 0 because this is expectation value. On an average, you're getting 0 signal at the difference between this and this. See, classically, you will expect this because you have light coming in one arm of the beam splitter, you have identical detectors here, you subtract the signals, you will get 0. That's what is happening actually. Expectation value of ND square. Now, ND square is here. So, this is mod alpha square. What is the expectation value of A1 dagger square? Zero? Zero, yeah, Rasool.
Sir, in this statement, this expectation value of ND square, if we again put theta is equal to 0, can't we get x square?
This is related to x theta. This is actually expectation value of x theta square.
No, suppose if we put theta is equal to 0.
Yeah.
So can't we get x square?
Expectation value of, yeah. I'm just keeping theta in general and I will tell you what happens. Theta is equal to 0 is x square, theta is equal to pi by 2 is y square automatically. So I could have done it here, but I'm continuing with theta and later on, for example, for coherent state, you will see theta doesn't come into picture at all. Whatever theta you choose, it's independent of theta. But in squeeze state, it may depend on theta. So you can choose different values of theta to calculate, okay? So what is NT square A1 dagger square expectation value? This is 0, A1 dagger square 0, which is 0. Second term, A1 square expectation value 0. A1 dagger A1 also 0. There is no signal, but there is a variance. So delta n square, delta ND square is ND square minus ND square, which is and this variance is actually coming from the coherent state that you are inputting into the beam splitter. So if you were to plot as a function of theta, so what I will do experimentally is choose one theta value, measure many times the signal that I'm getting. That signal can be positive or negative. With this variance, I change my theta. This is independent of theta. So as I change my theta, if I can scan my theta, for example, for time, I will measure constant variance. That means the signal that I'm getting as a different signal is fluctuating, and the fluctuation is given by this variance. What is the variance of a coherent state? Mod alpha square. This is exactly the variance of the coherent state that I'm measuring in this example because I'm not putting any signal on the other arm 1. Now let me go to a squeezed vacuum state.
The coherent vacuum state would have no variation.
No. No variation meaning?
Only a coherent vacuum state.
Yeah. In the number of photons, but not in the electric field. If you calculate the electric field, there is variance. Yeah. Okay, how do I define squeezed vacuum? Where B is defined as it is a state which satisfies this equation where B is an operator given by mu A plus mu A dagger. Next class I will show you that the output from a parametric down converter, a degenerate parametric down conversion process with no input at omega generates this kind of a state. Now from here you can actually calculate, which we have done earlier, mu b minus nu b dagger, because we need expectation values of the various quantities. So first let's calculate. So what I'm getting is, now this is squeezed vacuum state coming from here, and this is alpha state, and I'm measuring in 3 and 4. Expectation value of ND, 2 mod alpha 0s a1 e to the power minus I theta plus a1 dagger e to the power I theta by 2 anyway, let me cut this 2 off. I will have 0s a1 is mu b minus nu b dagger plus, no sorry, into the e to the power minus I theta plus 0s mu b dagger minus nu b 0s e to the power I theta. I am assuming mu and nu to be real, just for simplicity. What is the value of this? B times 0s is 0, b dagger times 0s is 0, b dagger times 0s is 0, b times 0s is 0. So this is 0. No signal. The different signal gives me 0. This is squeezed vacuum. Please note, we have discussed earlier, squeezed vacuum is not empty. There are photons in squeezed vacuum, because if you calculate the expectation value of A dagger A in the state, it's finite. And now I need to calculate expectation value of ND square, and for which I would need, so expectation value of ND square, for which I will need expectation value of A1 square, expectation value of A1 dagger square, expectation value of A1 dagger A1. Now we have done these before, so let me just recall and give you the expressions which we will use here to simplify. Well, let me give you for which we have done before, for a general squeeze state. This is equal to beta square mu minus nu whole square minus mu nu. This is equal to beta square into mu minus nu whole square minus mu nu. This is equal to beta square into mu minus nu whole square plus nu square, where b beta is the eigenvalue of this equation, and for squeezed vacuum beta is 0. Okay, so for squeezed vacuum we have derived these equations in an earlier class. For squeezed vacuum beta is equal to 0, so expectation value of A1 square is minus mu nu, expectation value of A1 dagger square is equal to minus mu nu, and expectation value of A1 dagger A1 is equal to nu square. These are the 3 quantities which I would need to calculate the expectation value of ND square. Yeah. So let's calculate now the expectation value of ND square. So here's the expression. So expectation value of this is expectation value of ND square. Mod alpha square exponential 2I theta. Expectation value of A1 dagger square is minus mu nu, we have just now calculated. A1 square expectation value is also minus mu nu. plus 2 nu square plus 1. A1 dagger A1 expectation value is nu square. A1 square expectation value is minus mu nu. A1 dagger square expectation value is minus mu nu. And this is the equation. So this is mod alpha square. Now I can replace one of the nu square. What is the relationship between nu and nu? So nu square is 1 plus mu square. Okay? So I will get mu square minus nu square is equal to 1. Mu square minus 1. So this becomes mu square plus nu square. 2 nu square minus 1 is mu square plus nu square. Mu square minus nu square is equal to 1. So 2 nu square plus 1 is equal to nu square plus mu square minus 1 plus 1. Simple algebra. Okay, so this is mu square plus nu square minus 2 mu nu cos theta, cos 2 theta. If I sum these two, I get 2 times cos 2 theta. Okay, so that's nd square. Expectation value of nd is 0. So what is the variance in the signal that's coming out from the difference? I will get delta nd square is equal to nd expectation value square, nd square expectation value minus nd expectation value square, which is equal to mod alpha square into mu square plus nu square minus. You saw a similar expression in squeeze state. So suppose, let me assume that mu and nu are both positive. Then if theta is equal to 0, delta nd square becomes mod alpha square into mu minus nu whole square. If theta is equal to pi by 2, delta nd square becomes mod alpha square into mu plus nu whole square. And remember, because mu square minus nu square is equal to 1, we had written mu as cos hyperbolic sigma and nu as sin hyperbolic sigma. So this is actually if I replace mu by cos hyperbolic sigma and nu by sin hyperbolic sigma, I can take care of the equation mu square minus nu square is equal to 1, and I get this kind of a relationship. And exactly what you see here is, what it implies is that the variance in the signal that you're measuring will now depend on the value of theta that I choose. If I choose my theta to be 0, the variance is less than mod alpha square. If I choose theta equal to pi by 2, the variance is more than mod alpha square. So if I were to plot the signal that I'm getting as a function of phase, the expectation value is 0. I just now showed in squeezed vacuum state, expectation value of nd is 0. So the average will be here, and then as a function of time, if I vary theta from 0 to 2 pi, at theta is equal to 0, the variance is so much. So let me call this as pi by 2, pi, 3 pi by 2 and 2 pi. So at pi by 2, I have greater variance. At pi, I get a small variance. 3 pi by 2, again greater variance. 2 pi small variance. So Remember a similar figure I had shown from a research paper. So what it implies is that if you were to lock your input local oscillator phase to be 0, theta is equal to 0. That means phi is equal to minus pi by 2, because phi plus pi by 2 is theta. So by an appropriate choice of the local oscillator phase, I can reduce the noise in my detected signal much below what I would have got had I just put nothing in the beam filter. Please note, if I put nothing here and if I put only alpha here, this particular one has a variance of mod alpha square, because nothing is vacuum state, the current vacuum state. If I put in squeezed vacuum state here, then what I will see is these two, depending on the phase which I choose, will have a noise which is much below mod alpha square, depending on the amount of squeezing, which depends on the value of sigma. If I have greater squeezing, larger value of sigma, there is greater reduction in the noise that I can achieve. So let me tell you, experimentally, people have achieved more than 10 decibels of noise reduction, which is 10 times.
What is the difference between a vacuum state and a squeezed vacuum?
Sorry?
What is the difference between a normal vacuum state and a squeezed vacuum state?
The normal vacuum state satisfies A 0 equal to 0. It has no photons in any of the modes. I'm looking at a single mode. There's no photon occupied in that. This particular squeezed vacuum state satisfies this equation, where B is an operator given by this. This particular state has photons in it. And this state is generated, as I will show you in the next class, when I take an optical parametric process and shine in only pump light. If I take a crystal and I launch only frequency omega, and if I satisfy the phase matching condition for omega to omega by 2 conversion, classically I don't get any output, but I'll show you quantum mechanically that even if you don't put anything, I will get an output, which is the spontaneous parametric down conversion, and that light which is coming out actually is squeezed. It's called squeezed vacuum. It's not vacuum anymore. There are photons in it, but it's a state, special state satisfying this equation. So, of course, you have got reduced noise in one phase at the cost of increased noise in the correspondingly opposite phase, different phase. So, depending on the value of nu and mu, and you can actually have squeezing at different times, and this is squeezed vacuum. One can actually go into a squeezed state, which is not a squeezed vacuum, but a general squeezed state, where the expressions which I have given here for expectation values a square, a1, a square, a dagger square, and a1 dagger a1 is given. And if I don't put beta is equal to 0, I will get a figure like this. In fact, what I will be able to show you is if you take a general squeeze state, you will get the expectation value will now be not 0, but it will go like this. It will be a larger noise here, smaller noise here, larger noise here. So there is a finite signal. There is a finite signal instead of being 0 as in vacuum. It is a sinusoidally oscillating signal, but depending on the phase theta which I choose, I can actually detect much reduced noise. So squeeze states are very interesting from this point of view, and they do find applications in essentially interferometry or for detecting very small changes of phase and so on and so forth, because there is much reduced noise from a simple laser beam that is coming out of a laser, which is a coherent state. The beam from a laser is a coherent state. I can generate squeeze states by a parametric down conversion process, and that squeeze state has reduced noise in one quadrature compared to the other. And that reduced noise I can use for signal processing applications. Yeah. Yes.
phi is constant or it is omega t minus kz?
No, this is only the phase of the alpha. Omega t minus kz is a separate term. This is the eigenvalue of A. So that A which I am using there is the time independent part of the annihilation operator. If you go back and look at the discussion on squeeze states, in coherent state that we had written A alpha is equal to alpha alpha is without the time dependent part. So in the Heisenberg, okay, where the operators are varying with time, but this particular one, this is the eigenvalue of A at t is equal to 0, for example. This is not the time dependent part. So that's the fixed phase of the local oscillator that I can choose by varying my input.
How can this reduced noise be used in applications? One of the applications of this system setup we have discussed is to characterize the input right from port 1. If we have a reduced noise at, let's say, theta equal to pi by 2.
See, for example, in this in the Mach Zehnder interferometer, I input only light in one of the arms, but the other arm there is vacuum. I put squeezed vacuum. Now what's going to happen is the interference is going to take place between your input state and the squeezed vacuum. And by using balanced homodyne detection at the output, I can use this reduced noise that is present in one quadrature of the squeezed vacuum, which is coming at the input of the Mach Zehnder. So I can have much better sensitivity of phase changes detection. Suppose I have in one of the arms of the Mach Zehnder, I have a device whose phase is changing with some parameter. I can detect that phase change much more accurately by using squeezed vacuum in the input of the...
At a particular phase of the input coherent plane.
Yes. I have to choose parameters so that I detect light corresponding to the phase with reduced noise.